Please go ahead.
So, good morning. My name is Amanda and this is my colleague Rajini. Our team is joining from Sri Lanka to introduce you to this SciFlow project using Parsl to execute scientific workflows on HPC clusters. And before I begin, I'd like to thank Kyle for inviting us to be a part of Parsl Fest 2020. This is our first time. We're very honored. So we are a team of undergraduates from the University of Colombo School of Computing. The SciFlow framework was developed as a final year software engineering project, primarily utilizing the Go programming language and Parsl. And now I'll provide like a quick introduction to our project. The idea behind SciFlow originated from workflows, which are commonly observed in the scientific domain. Most tasks that we as researchers and analysts perform are easily expressible as workflows. So these workflows provide abstraction, integration, and reusability, and thereby easing the process of scientific knowledge discovery. The complexity of the workflow increases proportionately to the complexity of the problem, and such applications require complex workflow connectors. SciFlow provides a set of compositional connectors in a control thread, which can be used to construct a variety of workflow patterns. The framework focuses on dynamic decision-making, where the outcome of an intermediary workflow component would be used to decide the path the remainder of the workflow would take. And we succeeded in separating computational components from coordination components by writing a separate control thread with Golang to provide easier workflow modification and component reusability to users. And by doing this, we also intended to provide programming flexibility through a layer of abstraction. And the intention was further reinforced by the use of Parsl, which hides the complexities of cluster computing to the users. So in summary, SciFlow brings forth a new programming paradigm, which combines Golang's control-driven coordination and Parsl's implicit parallelism to produce controlled implicit parallelism. A SciFlow workflow is constructed by stringing together individual Python Parsl computational units coordinated by a Golang control thread using a concept we call connectors. And this diagram depicts the simplest of connectors available in the SciFlow framework. The sequential connector is used in instances where the control simply passes from one component to another. When a computational module completes its task, a signal would be sent through a Golang channel to the control thread, and the control thread would then pass the signal to another channel based on the defined control logic, which would in turn trigger the next computational component into execution, also known as event-driven coordination. And this connecting bridge between modules is what we call a connector. We provide the implementation of 7 such connectors, including those catered towards AND gates, OR gates, XOR gates, and loops. These connectors provided within the SciFlow framework are generalized and also reusable. And this slide shows an abstraction of the core functionalities of SciFlow. Using the previously mentioned channel connectors, the user is able to connect computational components in a multitude of workflow patterns as suited to his application. The workflow displayed here makes use of 3 types of connectors. One for sequential execution, another for splitting the coordination thread into parallelly executing modules, and another one for dynamic decision making. With dynamic decision making, the workflow could be automated to run a number of times parallelly with different parameters. Connectors can be used to select the best performing parameter set based on some performance metric. And based on this selection, the workflow path would be modified at runtime to yield better quality results. With Parsl's implicit parallelism, we are able to orchestrate the entire workflow on any HPC resource.
All right. The scientific workflow applications that SciFlow caters to make use of large data sets. Therefore, we use both data and task parallelism to improve computational efficiency within SciFlow. The framework executes computational modules concurrently using the Golang control thread, thereby providing task parallelism. This proves to be extremely useful in situations similar to hyperparameter optimization. Using SciFlow, the user has the ability to divide the dataset either horizontally or vertically as suited to his application, and this would emulate data parallelism. We were able to deliver this functionality, that is data parallelism, through the developed framework by integrating the Parsl library. We consider domain experts and scientists to be our target audience. So such users often do not possess the skill required to harness the full potential of cluster computing. Therefore, we intended to create a framework where HPC resources were easily accessible to these users without the inherent MPI programming burden involved. Parsl provides such a layer of abstraction. Through the use of the Parsl library within SciFlow, we enable the users to better focus their energies on domain-related applications with a lower learning curve for HPC. The use of Parsl within SciFlow is twofold: to perform data parallelism on individual computational components and to provide execution location independence to its end users. Scientific computing applications generally work with large data sets. The benefits of data parallelism in such scenarios were apparent to us from the significant reduction in the processing time. With Parsl, we were able to easily scale out our scientific workflow applications with minimal effort. We started with threads on a local computer, and then we moved to a Beowulf cluster with a few simple code changes. So Parsl's execution location independence allows its users to start small and grow as the project progresses. Parsl fit perfectly with one of our project objectives, which was to provide a layer of abstraction for cluster computing. We commenced our project with the parallel scripting language Swift. A few months into the project, we stumbled upon Parsl at the Argonne National Laboratory website. And Parsl proved to be a better fit for us owing to its Python integration, which is well suited for scientific computing. It has been helpful if the connection between Swift and Parsl was clearly stated on the Swift website. SciFlow is an undergraduate project, so while working with Parsl, we came to realize the ease of integrating this technology to any project, irrespective of its complexity. Additionally, we found the Parsl team to be extremely responsive and helpful in resolving some of our GitHub issues. This was extremely important for the success of our project. To end our presentation, we'd like to extend our gratitude to the Parsl team for developing this library and making HPC so easily accessible to the community. So if there are any questions, we'd be happy to answer them now.
That was a great talk. I had no idea that the project was built entirely by undergrads. That's amazing. So we just happened to find this on GitHub. So for those of you out there that are interested in SciFlow, if you Google it, you'll find on GitHub they have a very nice package, and they even have a great deal of documentation. Very impressive. That's all I wanted to say.
Thank you very much.
Yeah. So you've got this stuff. You've got some stuff running in Go, and then all the Parsl stuff is in Python. How are you interfacing those together?
So our individual computational modules are written with Python, okay. And we can parallelize them either horizontally or vertically within the module. That is data parallelism, and then we also provide execution location independence through Parsl.
So Go comes in to control the entire thread. It's not integrated per se.
Okay. So the Go stuff launches a Python script or what?
It launches a Python script, and it kind of like controls the direction the workflow would take. Yeah. It's the control logic.
Yeah. Okay.
We are trying to separate the control logic from the computation.
Yeah. Cool.